All right, let's dive into a classic chemical mystery, a real whodunit that you might find in a chemistry lab. We're cracking the code on aldehydes versus ketones.
So picture this. Someone hands you a test tube. Inside is a clear, mystery liquid. They tell you it's one of two things, an aldehyde or a ketone. The problem? They look the same, they can smell the same, and chemically, they're practically identical twins. So how in the world do you figure out which one you're holding? The whole reason they're so tough to tell apart comes down to one shared feature, a kind of chemical fingerprint that they both have, and that's the carbonyl group. It's just a carbon atom with a double bond to an oxygen atom, and it's right at the heart of both of these molecules.
And right here, this is the tiny, tiny difference that changes everything. See, on the left, an aldehyde has its carbonyl group stuck on the end of a carbon chain. That means it's always bonded to at least one hydrogen atom. But look at the ketone on the right. Its carbonyl group is always sandwiched right in the middle between two other carbon atoms. This little detail, that's our key to cracking the case.
Okay, so before we even try to tell them apart, we have to do our due diligence. We need to confirm that our unknown chemical even has a carbonyl group in the first place. Think of it as making sure our suspect was even at the crime scene. For that, we use a general catch-all test.
Our first tool is a bit of a mouthful. The 2,4-dinitrophenylhydrazine test. Yeah, let's just call it 2,4-DNPH for short. This chemical is basically a carbonyl-seeking missile. It's designed to do one thing: find that carbon-oxygen double bond and react with it.
So, we take our mystery liquid and add some 2,4-DNPH. If we see this yellow solid suddenly appear, what we call a precipitate, then, bingo, we've confirmed it's a carbonyl. But here's the catch. As you can see, we get that exact same yellow solid for both aldehydes and ketones. So we know we're on the right track, but we still don't know who our culprit is. The plot thickens.
Okay, so to recap, our first test worked, but it was too broad. It told us we're in the right chemical family, but it didn't give us a specific name. To really solve this, we've got to bring in the specialists. Tests that are way more picky, tests that will only react with one of our suspects.
And this is where the real fun begins. It turns out there are a bunch of tests that only work on aldehydes. And why is that? Well, remember that lone hydrogen atom hanging off the carbonyl group in an aldehyde? That little hydrogen is like an Achilles heel. It makes aldehydes super easy to oxidize, while ketones, protected by carbon atoms on both sides, are much tougher. These next tests take full advantage of that weakness.
First up, we have Felling's test. You start with this really beautiful bright blue liquid. Now, if you add an aldehyde and warm it up a little bit, you get this incredible transformation. The blue solution turns into this fiery brick red or orange red solid. It's impossible to miss. But what happens if you try the same thing with a ketone? Absolutely nothing. It just stays blue. It's a total dead giveaway.
Now for what is, hands down, the coolest looking test in the playbook, the Tollens test. People call this the silver mirror test, and for a very good reason. When you add an aldehyde to the Tollens reagent, a chemical reaction happens that actually creates pure metallic silver. And that silver coats the inside of the glass, forming a perfect, shiny mirror. It's an absolutely unmistakable sign you have an aldehyde. A ketone, once again, does not.
And our last big test is called Schiff's test. The reagent itself is totally colorless, looks just like water. But if you add even the tiniest drop of an aldehyde, it bursts into this brilliant violet magenta color. It's an incredibly sensitive test, great for picking up even trace amounts. And by now, you can probably guess what happens with a ketone, right? Nothing at all. The liquid stays clear.
Okay, we've collected all our evidence, we have our general test, and we have our super specific tests. So now, let's put it all together into a foolproof step-by-step strategy. This is exactly how a chemist would solve this puzzle, every single time.
So here's the game plan. It's just two simple steps. Step 1, use the 2,4-DNPH test. If you see that yellow solid, you know you've got a carbonyl, so you can move on to step 2. For step 2, you grab one of the specific tests, like Felling's solution, add it in and heat it up. If you see that fiery orange-red precipitate, bam, you've unmasked your aldehyde. And if the solution just stays blue, well, by process of elimination, it has to be the ketone. Case closed.
This is all really cool, but you might be thinking, okay, why does this actually matter outside of a chemistry class? Well, it turns out this same chemical detective work is used to identify some of the most basic molecules in our lives, including the stuff we eat.
You remember Felling's test, right? The one that goes from blue to orange-red? Well, that test is a classic way to spot certain kinds of sugars, what we call reducing sugars. Glucose, for example, is what's known as an aldose. It's basically a sugar that has an aldehyde group on it, and because of that, it gives a big positive on a failings test. This simple reaction is super important in fields from food science, for checking sugar content, all the way to medicine.
When you stop and think about it, it's pretty amazing, isn't it? A simple, visible change, a flash of brilliant color, or the sudden glint of a silver mirror can tell you the secret identity of a molecule you can't even see. It just makes you wonder, in a world full of invisible chemistry, what other incredible secrets are just one simple test away from being discovered? Thanks for tuning in.